Mr. Lee, and today we're going to go learn about Coulombs Law. Now, I was thinking to myself, who better to teach you about Coulombs Law than Mr. Charles de Coulomb himself? So let's go find him! Whoa! Merci beaucoup, Mr. Lee. I am Charles de Coulomb. I am a French physicist, and I will teach you about how I discovered my law, the Coulombs Law. One day I was in my lab doing my experiment du jour. I got a ball, and I got another ball, and I charged the big ball. And I brought the big ball to small ball, and it moved. Did you see that? It moved. Ha! And then I got famous. You see, I'm a genius. Now, from that experiment, I came up with the equation. I said, the force between two charges is determined by how far it is from each other. Now, what is K? I'm the K. That's my constant. K is equal to 9E9 Newton meter squared per Coulomb. Named after me. I did it. Wow, thank you, Mr. Coulomb. Now, let's go over how he came up with that equation. To start us off, let's do a recap of what we know about electricity. First off, there are two types of electric charges. We have the positive and the negative. Second thing that we know, like charges, aka positive and positive, or negative and negative, they will repel from each other. Contrary, unlike charges, positive and negative, when they're next to each other, they will attract to each other. And last but not least, this is something that Mr. Coulomb found out himself, that the further away the charges, further the distance, the weaker the force. That is something new. So we know the Coulomb's law. It's very important that we realize the analogy between Coulomb's law and what we use for the universal law of gravitation. In fact, if you put them side by side next to each other, they look almost identical except for the variables that we use. So here is Coulomb's law as we know it, and right here is the universal gravitation law. And if we take a look at it, it's pretty much identical. Instead of masses, we have Q for charge, and we have the same R for the radius or the distance away from the object. Now, the most important part about this is the constant. Coulomb's constant is a lot bigger. In fact, Coulomb's constant is 9 times 10 to the 9 compared to the gravitational constant, which is 6.67 times 10 to the negative 11. Very tiny compared to Coulomb's constant. So what we can say is that the electric force between two charges is a lot stronger than what the gravitational force is between those two charges. Now that we have the law, let's determine how the different variables interact with each other. So to start us off, we need three things. We need two charges that are separated by a distance away from each other. So now let's think about it. If we have two charges and we want to make the electric force between them smaller, so we want to decrease the force while keeping the two charges the same, what we have to do is increase the radius between them. Okay. Now, we can also do this in the reverse order. If we want to increase the force of attraction the two charges have, or the force of repulsion the two charges have on each other, we want to increase the force. What we can do is decrease the distance that they are away from each other. When two charges are closer together, they'll exert a stronger force on each other. Now, let's say we have a set distance that we know of. So r squared is constant. And we want a strong force between one charge and another. Let's say our first charge, we already know what that value is. In order to increase the force that charge 1 feels, we must put a strong charge, or increase the amount of charge that is in charge 2 in order to increase the force that the two feel on each other. Now, you might be noticing that when I describe the forces, I'm using them, or I'm describing the two forces or how they enact on each other. So what that means is we can still use Newton's third law. For every force, there's an equal but opposite reactionary force. So if charge 1 is pushing on charge 2 must push on charge 1, and vice versa. If charge 1 is pulling on charge 2, charge 2 must pull on charge 1 as well. Now that we have our equation, we can determine the relationship between the variables and how it will be represented in graphical form. So for example, we were to do a lab, how would we graph our data? Or what should the data look like? Here in our y-axis, we have f of e, or the e force between the two charges, and in the x-axis, we have the r, or the distance between the two charges. Let's say we have two like charges. If we have two like charges, q1 and q2 are both positive, then the closer they are together, that means the force between the two is very great. However, because it is r squared, the further apart that they go, the force of attraction or the force of repulsion between the two gets weaker and weaker exponentially. So the further out they go, it'll be very, very weak. And we have 2 points. 1 point to show that they are super repulsed by each other because they're so close, and they're not as repulsed by each other because they're far away. We get a beautiful curve like that. Now, if we were to do the same idea but with two different charges, one positive, one negative, the closer they are together, the force of attraction is so great. And for us, the force of attraction is determined by a negative sign. So if we have a positive charge and a negative charge, the force of attraction is very strong or very negative. However, if you separate the two, then the force of attraction becomes weaker and weaker. In fact, it gets exponentially weaker. And so if we were to plot our data and create a graph, we will get something like this. This is the mirror opposite. Okay? Now, what if we were to get the same graph or the same data and we were to linearize it? Now, remember, we linearize data because it helps us find the slope, or it helps us actually see what's happening. So let's predict. If we have a graph like this and we want to linearize it, we have two positive charges. When the two positive charges are super close to each other, we can say that the force of repulsion between them is very great. And the further out they go, the force of repulsion between them gets weaker and weaker and weaker. Eventually, they're going to be so far apart that there's going to be no force between them at all. And so what we get when we linearize the data is a straight line. Now, you might be thinking to yourself, hold on, that didn't make any sense to me. How come when they were super close, your data point is all the way out there, but when they're super far, the data point is right there closer to the zero? That doesn't make any sense, Mr. Lee. Now, in order to explain this, let's come up with a chart. Okay, so here is my force of attraction / repulsion, the radius between them, and the 1 over radius squared chart. Now, let's say we have a very small radius. Let's say it's 1 over 10. So if our radius is 1 over 10, when we put it into this equation, we get 1 over 10 squared. And when we do that, we get 100. Wow. So let's go the opposite direction. Let's say the two objects are very far from each other. Let's say it's 10 meters away from each other. Wow! So when the two charges are 10 meters away from each other, and we put it into the 1 over r squared equation, we get 1 over 10 squared, which is 1 over 100, which is 0.01, which is super close to 0. So you see, the further away the objects are for this kind of graph, the closer it will get to the 0 point for the x-axis. However, the closer the two charges are actually together, because of this inverse squared relationship, the further out on the x-axis it'll be. Now, the last kind of graph that you might see is the force of attraction on the y-axis and the charge on the x-axis. What this means is, if the charge gets stronger and stronger, what's going to happen between the force of attraction / repulsion between this charge and a charge that is a constant? And we know that the stronger one charge gets, the force overall gets stronger and stronger. All right, now it's time to do some math. An example problem. Let's say we have two charges. We have one positive 20 microcoulombs, and we have one negative 10 microcoulomb charge. What is the force between them? In order to solve this, we need to know the distance between the two charges, which I gave us as 20 centimeters, and this Coulombs Law equation. Now, see if you can use the variables that we were given to solve it yourself. If not, I'll guide you through it. First off, always start off with the basic equation itself. Then you want to fill in the variables. All right, so this is the written form of the equation. Now, a couple of pointers here. I like to use 9e9 or 9 times 10 to the 9 for k. You might see it written as 8.999999999, but I like to use this one. Also, micro is the prefix for 10 to the negative 6. And so you'll notice here I wrote 20 times 10 to the negative 6. Okay? Because we have a negative charge, I put in a negative 10e to the negative 6. And most importantly, down here, we need to be sure that we are in SI units, meaning the centimeters you have to convert. And remember my rhyme. In order to go from centimeters to meters, move it over to, and that's how we get 0.20. Now, the part that the students get wrong the most is they forget to square the radius. So I put a little square right there.